Now coming to the second subgroup test, which is known as two step subgroup test, right? So it states a non-empty subset, a non-empty subset H of a group G is subgroup of G if and only if two conditions are satisfied. Okay, first is if it is closed in H, that is AB belongs to H for all A comma B belonging to H, or it can be also written as AB belonging to H implies AB belongs to A into B belongs to H, right? Secondly, second condition is A inverse belongs to H when A belongs to H, or you can say A belongs to H implies A inverse belongs to H. So this is the second. If these two conditions are satisfied, then we say this this given subset of G is subgroup of G, right? So we are going to prove this, and proof is very similar to one step subgroup test, right? So I'll be not going in detail, I'm just overviewing the proof. Okay, so firstly let G be a group and H be subset of G which is non-empty, right? So first thing first, necessary part, because we are having if and only if statement. So firstly we are going to assume this statement, and we will prove this statement. In sufficient part we are going to prove this statement, and we are going to prove initially the initial statement. Okay, so necessary part in this, assume that H is subgroup of G. So what we are going to prove? We are going to prove that if H is subgroup, then these two conditions are satisfied. So if H is subgroup of G, this implies H is group in itself. By definition, obviously H is group in itself. Okay, since H is group in itself, therefore it satisfies all four properties of a group, right? It is closed. Also inverse of the every element exists. So these two properties are nothing but closure property and existence of inverse. Therefore obviously AB belongs to H for all A comma B belonging to H because of closure property, and A inverse belongs to H for all A belonging to H, existence of inverse, right? Now coming to the second part, which is a sufficient part. In this we are going to assume these two property. Okay, we are going to prove that H is subgroup of G. Okay, so this is the important part, and we will be using this part in many examples. Okay, assume that AB belongs to H for all first, okay, A comma B belonging to H, or you can write it as if A comma B belongs to H, this implies AB must belong to H. And secondly, A inverse belongs to H for all A belonging to H. Or you can write it alternatively, like if H is belonging to, if A is belonging to H, this implies A inverse also belongs to H, existence of inverse. Okay, so let us prove the we shall prove that. Okay, write it also. We shall prove that H is subgroup of G. Okay, we shall prove that H is subgroup of G. Now, how we are going to prove this? Firstly, we are going to prove that, see, this is closed. Okay, this is closed and this is inverse also exist. Okay, so we just need to prove two more property, because already it is given that H is given that H is subset of G. So we just need to prove that, okay, it is non-empty subset. This is given in the hypothesis, right? So we just need to prove that, H is group in itself. For this we will have to prove all those four properties. Obviously these two properties are true, existence of inverse and closure property. So only two properties are left, one is associative property and one is identity property. Okay, so we just need to prove two properties here, okay, of group, because two property are already given. So one is existence of identity and another is associative law. So for existence of identity, you see how we are going to prove this. See, we know H is non-empty subset, right? We know H is non-empty, right? Therefore it does have one at least one element, right? Say it is H. So we know it satisfies existence of inverse, right, by condition 2, okay, which we have already assumed. So this implies, therefore A inverse also belongs to H by assumption or condition 2. Okay, condition 2, inverse, existence of inverse. Now you see H is closed. We have already assumed this in condition 1, right? So therefore A into A inverse also belongs to H by assumption or condition 1. Okay, so this implies identity belongs to H. Therefore identity exists in H, right? So now we are going to prove associative law. For associative law, how we are going to prove this? It is pretty simple, okay, right? Associative law, since H is subset of G, therefore all the elements of H are also elements of G. Therefore they obeys, since all the elements of H are elements of G, right? So all the elements of G obeys associative law because it is a group, right? It is a group. So therefore elements of H must obey associative law. Okay, therefore H holds associative law. Thus in this way all four properties are true for this H, right? Therefore H is group in itself, right? H is group in itself, also it is subset of G, therefore H is subset of a subgroup of G. So thus we have proved the theorem, hence the theorem. Okay, so now we are going to take some examples, okay, on one step subgroup test and two step subgroup test, right? So let me pick one example for you. It says let G be a abelian group, okay? Let G be an abelian group. Then, okay, show that all the elements of finite order in G form subgroup of G, right? Okay, so all the elements, okay, all the elements of finite order, okay, finite order in G forms subgroup of G. So see how we are going to prove this. Solution is this, okay, let G be a group, okay, you just write it by yourself. And now let us name this set H, okay, and H is a set which contain all the elements of G which are having finite order, that is order of X, all those X's whose order is finite, right? So we want to show that this H which contain all the elements whose order is finite in G, this forms a subgroup of G. So how we are going to do this? See, we can prove this using two-step subgroup test. Also we can prove this by one-step subgroup test. So see, if you want to prove this by using one-step subgroup test, we will have to take two elements from this set. For if you want to prove this by two-step subgroup test, then also you will have to take two elements from H. In this you will have to prove that if AB belongs to H, then AB inverse also belongs to H. And in this you will have to prove two conditions. One, AB belongs to H. Second, if A is belonging to H, then A inverse also belongs to H. So this you need to prove, right? So see how we are going to prove it. So by one step, so this is one step, okay, and this is two step. So in exam, if question comes, you just go by any one of these two, okay. So right, so two-step subgroup test firstly, okay. See, A comma B belongs to H. This implies H contain all those elements whose order is finite. Therefore order A and order B is finite, okay. Now what could be order of AB? Is it finite or not? Okay, let us check this out. So if order of A and B are finite, let us assume order of A is M and order of B is N. So if we raise power of AB by mn, okay, so this implies, since it is abelian, we can write a raised to power b mn and b raised to power mn because it is abelian. So it is equal to, we know order of a is equal to m, so am is equal to 0 identity, and m power anything other than this, okay, and m a raised to power m power anything is equal to e again. So same is the, therefore a mn is equal to e, so it is equal to e. Same is the case with b, okay, so it is equal to e time e, which is e. So it means order of AB is something which divides this mn, right, by the theorem. So it implies order of AB is either mn or it is smaller than mn, okay. Therefore we can say order of AB is finite, right. So it is finite. So therefore this implies AB belongs to H, right. So you just keep this thing in your mind that, okay, you just keep this thing in your mind, right, that this B belongs to H, okay. Now secondly, we want to prove that A inverse also belongs to H. Since we have already proved this, that order of A is equal to order of A inverse, and order of this thing is finite, therefore it must be also finite. Therefore order of A inverse is finite, right. So it means A inverse belongs to H when, okay, for all A belonging to H. So this is the second, second condition, right. So we have proved second condition also. So therefore we can write it as, therefore AB belongs to H when A comma B belongs to H, and A inverse belongs to H when A belongs to H. So thus by one step, two step, okay, two step subgroup test, H is subgroup of G, okay. So thus we have proved this by using one step subgroup test. Now let us come to the second part, okay. So how we are going to solve this? Okay, so in this we have to prove that we shall prove that AB inverse belongs to H, right. So see now, since A comma B belongs to H, this implies order of A and order of B is finite, okay. Say order of A is equal to M and order of B is equal to N, okay. Now since order of A is equal to order of A inverse or B inverse, okay, and order of B is equal to order of B inverse, therefore order of B inverse is also equal to, it was n. Okay, it is some other number n. So order of B inverse is equal to n, right? Now we want to show that order of AB inverse is also finite. So see what could be order of one second, let me drag this down. Now what could be order of AB? Okay, now we want to find out order of AB inverse. Okay, so now you see what is A raised to power A into B inverse power Mn. Okay, it is equal to, since it is abelian, so we can write it as A Mn B inverse power Mn. Okay, so it is equal to A Mn B Mn whole power inverse. Okay, so since as I already gave the reasoning why it must be equal to E, so same applies here also, E into E, which is equal to E identity. So therefore this implies order of A inverse is also is finite, which implies AB, which implies AB belongs to AB inverse belongs to H. Thus by one step subgroup test, H is subgroup of G. Hence we have proved that H is subgroup of G, right? So now a few more examples. Problem okay, so second problem, let G be the group, G be the group of non-zero non-zero real numbers under multiplication, that is which group I'm talking about, that is J is equal to R star, non-zero real number. Okay, it is not containing a real number. Okay, and what is operation is multiplication here. Okay, so this is the group. Check whether oh sorry, check whether, okay, check whether following 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 subset of G is subgroup or not. Okay, so subgroups are these. First subsets are these. First is H is equal to X belonging to G such that X is an irrational number. Okay, means H is nothing but set of Q complement. Okay, that is set of all the irrational numbers. Okay, and second, K is equal to X belonging to G such that X is equal to 1 or irrational number. Okay, irrational number. Okay, it is nothing but union of irrational number and 1. Okay, 1 is the only extra element in this. Okay, except irrational numbers. And third is M is equal to X belonging to G, okay, such that X is greater than or equal to 1, right? So let us disprove them one by one. First, here, okay, you can assume, you can say, we are given that G is a subgroup of real numbers under multiplication, that is G is equal to R star multiplication, right? So, and given subset here is H is equal to X belonging to G such that X is an irrational number, right? So my claim is, can you figure it out, is it a subgroup or not? So I say it is not a subgroup. Why it is not a subgroup? It is not a subgroup of G. Okay, that is H is not subgroup of G. Why? Because you see, if it has to be subgroup, it has to be satisfy all it has to be group in itself. Okay, for group in itself, it must satisfy all four properties: closure, identity, associative, inverse. Okay, but you see, 1 does not belongs to H. Why it doesn't belong to H? Because H contains all those numbers which are irrational number, but H1 is not an irrational number, therefore 1 does not belong to H. Since H1 is 1 acts as an identity when we are working under multiplication, so this implies existence of identity. Okay, this property is not satisfied by this group, hence you can write identity does not exist. Okay, so this, therefore H is not a subgroup of G. So second is second subset is K equal to X such that, okay, X is equal to 1 or X is irrational. Okay, X is irrational number. Okay, so see here, now identity तो इसमें है. Okay, no doubt identity डाली गई है इसमें, एक नया सेट बनाया गया है जिसमें irrational नंबर है और identity भी है. ओके, फिर भी ये ग्रुप नहीं होगा. क्यों नहीं ग्रुप होगा? बिकॉज इसमें कोई रैशनल नंबर आएगा नहीं. ओके, इसमें वो सभी नंबर आ रहे हैं जो इररेशनल है एंड 1 भी आएगा. ओके, बट इफ आई टेक, माई क्लेम इज दिस सेट डू नॉट सेटिस्फाई विच प्रॉपर्टी? क्लोजर प्रॉपर्टी. ओके, ये वाला सेट क्लोजर प्रॉपर्टी, इनफैक्ट जो फर्स्ट वाला सेट था H, वो भी क्लोजर प्रॉपर्टी सेटिस्फाई नहीं करता था. और ये भी नहीं करेगा, ठीक है। वाई इट डज नॉट सेटिस्फाई क्लोजर प्रॉपर्टी सी, वी नो रूट टू इज irrational number, so it belongs to k. what is multiplication of root 2 in root 2? कितना है 2, बट 2 तो इस सेट में है नहीं, क्योंकि इस सेट में सिर्फ वही है, तो ये क्लोज नहीं है, क्योंकि जब हम दो को मल्टीप्लाई कर रहे हैं, दो इरेशनल नंबर को रैशनल नंबर आया जा रहा है, पर रैशनल नंबर इसका एलिमेंट है नहीं, सो देयरफॉर इट डज नॉट बिलोंग टू क्यू, सॉरी नॉट क्यू सी बट के। ओके, दिस implies 2 into 2 does not belong to k, therefore k is not closed. Okay, now third, hence it is not subgroup of G. Now coming to the third set, M is equal to X such that X is greater than 1, इक्वल टू 1, तो इसमें आइडेंटिटी है, ठीक है, और ये क्लोज भी होगा, राइट, बिकॉज एनी टू नंबर विच आर ग्रेटर देन 1, ओके। जैसे दो कोई नंबर ले लेते हैं, 2 ले लिया, 10 ले लिया, जो दोनों ग्रेटर देन 1 है, तो उनका मल्टीप्लिकेशन कितना आएगा, और भी बड़ा हो जाएगा, वो और भी 1 से बड़ा रहेगा। सो ये क्लोज्ड है, आइडेंटिटी भी होगी इसमें, एसोसिएटिव भी होगा, और बट वन थिंग विच इज़ नॉट हैपनिंग इन दिस इज, फॉर एग्जाम्पल 2 ऑब्वियसली इट बिलोंग्स टू m, ठीक है, 2 m को बिलोंग कर रहा है बिकॉज 2 इज ग्रेटर देन इक्वल टू ग्रेटर देन 1, बट इसका इनवर्स क्या होगा, इनवर्स ऑफ 2 इज 1/2 ऑब्वियसली, ठीक है। सो बट 1/2 इज नॉट ग्रेटर देन 1, ये एक से बड़ा थोड़ी है, तो देयरफॉर 1/2 does not belong to m. It implies, okay, this implies inverse does not exist. So therefore again h is not it is not h, it was m, okay. So m is not subgroup of G, okay, fine. Now from this we have learned one thing, that if you want to prove that H is not subgroup of G, ठीक है, 3 चीज़ें चेक करो, कौन कौन सी, आइडेंटिटी चेक करो, उसमें आ रही है नहीं आ रही है, क्लोजर है वो नहीं है, ठीक है, क्लोज्ड है या नहीं है, या फिर उसमें इनवर्स है या नहीं है, बाकी एसोसिएटिव तो वो होता ही है, ठीक है, बिकॉज जितने भी एलिमेंट H के हैं वो सारे एलिमेंट G के होते हैं, तो इसलिए ये एसोसिएटिव तो होता ही होता है। तो अगर आपने डिस्प्रूव करना है कि सम सेट इज़ नॉट अ सब ग्रुप ऑफ G, तो आप उसमें से ये फाइंड आउट करो कि आइडेंटिटी या क्लोज्ड नहीं है या फिर इनवर्स उसमें नहीं है, ओके। सो इन दिस वे वी कैन प्रूव दैट अ सेट इज़ नॉट क्लोज्ड, a set is not a subset is not a subgroup, right? So now finally we are going to do one more theorem, okay, at last. So this theorem is finite subgroup test, okay. One second, I think it's enough for today. So we are going to end here only, okay. Finite finite subgroup test will be done tomorrow, okay. Thank you.